Hello, and welcome to our presentation. We are going to be speaking about how heat exchangers work, and we'll go through a few examples of everyday applications that we use them in. So, to start off, what is a heat exchanger? Well, a heat exchanger is a system used to transfer heat between two or more fluids, being liquid or a gas. The heat is transferred through the exchanger fluids that are separated by a conductive medium. When a hot object or substance comes into contact with a cold object or substance, the heat will naturally want to flow to the colder object. The heat energy exchanges back and forth until thermal equilibrium is reached. Thermal equilibrium is when substances reach the same temperature. There are three different types of flow. The first type of flow is co-current flow. Co-current flow is when the fluids flow in the same direction, as shown in the top left figure. The second type is counterflow. Counterflow is when the fluids flow in the opposite direction, as shown in the top right figure. The third figure shows crossflow. Crossflow is the fluids flow perpendicular to each other. Now the bottom right shows a hybrid, which is a cross between crossflow and countercurrent flow. There are three different ways heat is transferred. The first way is through conduction. Conduction is the transfer of heat by direct contact. Transfer occurs when molecules hit against each other. An example of this is a pan heating up on a stovetop. The second type of heat transfer is through convection. Convection is the movement of heat by a fluid or air. The fluid moves from one location to another, transferring heat along the way. An example of convection is the heat coming off a radiator that heats an old house. The third type is radiation. Radiation is the transfer of heat by electromagnetic waves. When standing in the sun, you are warmed by the electromagnetic waves that travel from the sun to Earth. Examples of radiation are light bulbs and toasters. We're going to talk about the types of heat exchangers. There are many types of heat exchangers, but we're just going to touch base on a few. We'll go through four examples. The first one is a double pipe heat exchanger. This type allows two liquids to cool down without mixing. This is the most simple and cheapest option, but is not the most efficient. The double pipe heat exchanger has two configurations. The parallel flow configuration has the main advantage is to get the temperature of each liquid to be the same. The two liquids run in parallel and both enter and exit the same side. The next configuration is the counterflow. This main advantage is better heat transfer compared to the parallel configuration. In the counter configuration, the liquids enter from opposite sides and flow head-on and exit at opposite sides. The double pipe heat exchanger is used in boilers and compressors. The next type of heat exchanger is the shell and tube. The shell and tube heat exchanger allows a hot liquid to pass through a cooler liquid without mixing. The cold liquid flows through the shell of the heat exchanger, and the hot liquid flows through the tube portion. The tube makes thermal contact with the shell. These are used in generators. The third one is a plate heat exchanger. This is made up of many thin metal plates to cool the liquid. It can be configured to allow the liquid to pass through multiple times. These are generally used in HVAC applications. The fourth one is a condenser type. This works by condensing a gas to liquid state. This is done by releasing the latent heat from gas. The removal of latent using a condenser allows the gas to condense into a liquid and still maintain the same temperature. The advantage of this is efficiency. and removing latent from a gas is more efficient than changing the temperature of the gas. This type of condenser is used in a refrigerator and AC units. So now we are going to go through an everyday example of a heat exchanger. So we have a short little video here. So an example of an everyday heat exchanger is a radiator in a car. The radiator in a car is a cross-flow type. So what we're going to do is we are going to give the motor fuel. It will cause the motor to heat up and the coolant to flow. The coolant will flow through the engine, gaining heat. Once the coolant reaches a certain temperature, the thermometer will open the mechanism to allow the coolant into the radiator. The hot coolant will enter the top and flow horizontally through the radiator. The cold air will flow perpendicular to the hot coolant. The coolant will flow to the bottom and exit at a cooler temperature. The coolant will then be reintroduced into the system to repeat. So as we can see in the video, we have a coolant temperature on the dash, and we are using a thermometer to measure the engine temperature. So if you look to the right, we have a little diagram showing the process on which it goes through. So as the motor is creating heat, you can see the coolant flowing into the top of the motor. The coolant will then take the heat produced by the motor, and as it circulates and reaches temperature, the thermostat will open, allowing the coolant to flow into the rad, which will enter through the top and flow down through the radiator. As the coolant is flowing down through the radiator, the cold air created by the movement of the car and the fan pulling in the cold air will cool the coolant down. As the heat transfer occurs, the coolant will then flow through the bottom of the rad at a cooler temperature and will return back into the system to repeat again. So in the video, we have a car that we are using as a demonstration. So we are giving it gas to heat up the engine so we can go and get the temperature and compare it to the coolant temperature. So the temperature of the motor is 22. Oh, it's going up still. So we are, I think it reached 24.6 degrees Celsius. So now we will take the 24.6 degrees Celsius and compare it to the coolant temperature, which the car will give us from all the sensors. And we're about 60 degrees Celsius. So at first, the temperature of the coolant increased quickly. As we can see, it went from 16.3 to 52 degrees to 74 degrees. And the temperature of the engine increased at a slower rate, as it went from 16.3 to 23.8 to 37. As the coolant got hotter, when it went from 74 to 93, a big jump, the engine temperature was able to increase faster because the coolant temperature was higher. So we have the time running. So the longer the car ran, the hotter the coolant got, which allowed the engine to increase in temperature. So using this flowchart above, we have label components found in a car that correspond. So the set point on our diagram here would be the engine operating temperature. Our error detector would be our ECU of the car. Our error signal would be the engine temp above operating temperature. Our controller would be the ECU, which turns the fan on and off, also indicates if the engine is overheating. Our actuator is the fan and water pump. Our manipulated variable would be our coolant. Our controlled variable would be our engine temp and our coolant temp. Our measured variable would be our engine temp and our coolant temp also. And then our feedback signal would be our temperature sensors within the car. We have a list of resources that we used throughout our documentation.